Okay, Z, I'm gonna just make this video and try to go through each of your questions. Hopefully, this is the best way to do this. Um, let's see. Sorry, I'm just reading through. Yeah, maybe I'll do because so here's the thing. You have a number of questions. I'm trying to organize them. Yeah, the first thing I think we need to clarify is that it is true that each of these blue cells should have an equation. So you can use these as a map. And what I've done here is I've said, okay, I'm going to give you a bunch of terms and definitions, and then you'll use those. You'll apply them when you're trying to finish the modeler. So let's just look at this first one. Um, but then you have to understand the theory too. So I know there's a lot going on. So our modulus of elasticity, E, is 29 million. I've given you that. That's for steel A36. It's a kind of steel. Then we say, okay, what is ES? So I'll look that up. ES is the derated modulus of elasticity. And what that was is we said that, so here's the steel derating factor. We said that, so ES is here. It's connected to this. That may be a little bit confusing if you haven't been keeping up, but I'll explain anything to you that you need. We derate the steel if we're within a certain distance of the ocean because I just made this up to try to create some variables, but saying that, if the steel is going to be corroded more quickly, we should give it a weaker strength than it's rated at. So the 29 million is the rated. So I'm going to create a variable here that allows me to derate this. So what would I do? First of all, you don't have any of your cells named, and you want to name them. So if I go to, and I'll show you. So formulas, name manager, there's no names here. If I go to this cell and I right click on it and say define name, I can name it E. That's what I want to name it. I'm going to change this to I want this just on the methodology page. Say OK. Now if I come here, I delete your equation. Oh, actually, and then I want to name this cell too. I'm going to name this S. And of course, you can just stop the video and do each of these things individually. So I've named this S. Now I want to make an equation equals E. E shows up. That's so I type in a letter and it accesses an alphabetical list of equations that are available or variables. And I just created that one, so it's there. I'm going to say E times S. And there's S, showed up like I wanted. And I'm going to divide by 100 so that because I'm using percent. And there you go. I've got my actual calculation of that 26 of my ES. Now, if I change this to 100, it's going to change back to the original, right? So now we have that set up, and that's the full workflow. We've got now an input, which is the orange cell, tied to just a constant essentially, and it's creating this variable. Okay, so that's the first thing that I think you need to understand. And so then you should go through and just try to understand every single one of these blue things, blue cells, and decide what goes in there. So you know that this is an equation. Um, so for example, here, let's name these. I'm just going to name this MA. Always make sure that you set it for just this page because we have multiple pages. Um, if I set it just for workbook, it would be that cell. Anytime I typed in MA, that would access that cell for any sheet. I don't want that. Um, I don't even know if I'm not going to worry about naming these. You can do that yourself. But see, the naming really helps because now I can see what this formula is, right? But so if I want to, so this is PD. Let me look up PD. That's the dead load, which means the weight of the slab. The weight of the slab is going to be its area, which is MA. If you look that up, is the modular floor area. So the modular floor area um, times the thickness of the slab TH, times its density, it's going to give you its weight, right? Because it's length times width times depth, so that's cubic, times pounds per cubic feet equals pounds. So rather than 64,000, we're going to say this cell, which has been named, times this cell, which you should name, but I didn't name, times this cell. And now we got our 64. Now we have our 64,000. But if I wanted to make this slab more dense, I could just adjust it that way. Very simple. I'm going to hit Control Z to go back. So that's the basic workflow. Okay, now let's look at some of your specific questions. You wanted to clarify that pStore and pSnow are design inputs based on region, so they don't have equations. Correct. So, oops. So these are just numbers you type in because they're orange. So I've tried to make this really straightforward. These come from here, right? The regional loads for both snow and storage. That's a code saying you have to build, if you're building a warehouse in the east of the United States, you have to design it to be able to take 100 pounds per square foot of live load. In other words, furniture, people, um, things you're storing. So I call that pStore region. But then over here, we have a calculation because it's blue. What's the pStore going to be for the live load? Well, it's going to be just the area again times the regional load. Now, again, I would name that cell. Let's even go do that. Um, but now we have an equation. So if I change this to 200, it changes my live load. But remember, you want to name this cell. So I'm going to hit define name. Maybe call it piece. I think yeah, maybe that's fine. I don't know what I called it in my actual thing. Um, oh, and I didn't name that correctly. Let's go. So now I'm going to Formula Names Manager. Here's all my names. You see, here's one that's workbook. Unfortunately, I have to delete that because it doesn't let you edit that. So I'm going to go rename that. Oops. I'm going to say define name. So I right click if I didn't make that clear. Methodology. Okay. And now if I come here, I can see these are all my name cells, and this is what they refer to, and their scope, which means which pages they are, sheets they are connected to. So now, so that's set up. So we do the same thing for pSnow, which is going to be the area that the snow is going to sit on times its pounds per square foot. Okay, so that answers this question, I think, right? Which is what? Um, pStore and pSnow are design inputs, correct, but they tie into um, pStore and pSnow. No, okay, so you have make sure that you understand this. Then pStore is the pounds per square foot, and pStore regional, and pStore is the load on the entire floor. So it's the area times, so it's feet times pounds per square feet, which is going to be pounds. Hopefully that's clear. If not, you can ask me again. Okay, what else do we have here? Where does the moment of inertia equation comes from, right? That's a big one. Now, then you basically ask me every single input, that's fine, but let's go step by step here. Let's not worry about SR, LUCR, and SRCR yet. Um, and I know it's difficult for you in class. I wish you would be able to ask me questions in class, but I guess it's just not going to work that way. So we do need to find a quicker way for you to ask specific questions. Um, okay, anyway, so where did I get the moment of inertia equation from? This is back to my modeling because I've written this down. Remember, so here's the Euler equation. This is the equation for a long slender column, the relationship between its failure load, that's the EPCR, PCR is critical buckling load, um, and then it's a simple equation, pi squared. E is the Young's modulus, which we've already defined as 29 million. I is a an equation unique to a specific cross section. If you don't understand that, you need to look back at other videos or ask me specifically to explain that again, and I can do it. Um, KT is the end condition, so that's either 1 or zero point 0.5 here, and LU is the unsupported length. Those are all actually, um, they're in a video. If you go back and look at the assignment, I maybe should have opened that up. There's a video that shows those. I'm going to move on. And if you have a specific question about that, you can ask me. But what I wanted to show you was now that if I rearrange this equation, see, because in the EPCR here, I know all of these things. I'm going to define the EPCR, the load, because that's going to be defined by the region that we're in. It's going to, in the amount of snow, and the way the concrete is designed, so how heavy the concrete is. So we'll know this load. We know pi, of course. E we look up, we've already got it. KT we determine based on whether or not it's a bolted or a welded connection. LU we know is 156 because that's the height of the column that we need. That's the column that we need to make the right ceiling height. So the only thing we don't know is I. Um, Yeah, I feel like I should explain this in a different way. But anyway, because I have another, there's a video of this that I made that shows this whole process. But if, so then if we solve for I like this, right? So I've just rearranged this equation to be this, then we know all of these numbers, P design, which is, the P design is the EPCR, the design, the load we think the column will take times a factor of safety. um, times a. So we know this, we know KT, we know LU, we know the adjusted strength, and we know pi squared. So then we can get an I value. So that's what this equation is here. And once we get that solved, anytime I change an input here, it changes my I value, right? Which then, and we use this I value to solve for the outer dimension of each of our columns because every column profile has a unique moment of inertia equation. So in this case, the moment of inertia equation, I equals OD to the fourth divided by 12. You can look that up. I've given it to you. So that's this equation here. Once we get, so we use this to get this, right? See that here. Then we just continue on. Once we have the outer dimension squared, for a solid square is the area. Then area times length is volume. We use the full length, which is what's called the cut length, which is the unsupported length is what's actually buckling. The cut length is the full thing that you buy. Um, and then the volume times the mass, um, times the density is the mass. And so we have the density over here that I've given you. Actually, that's not the right density. Did I just change that? Yeah, it's 0.3. What is it actually? 0.284. Sorry. Let me fix this. Okay, this is 0.284. So mass density, and then cost per unit, which is 77 cents, times the mass is the cost. So that's the flow of equations. I'm sorry, the flow is from moment of inertia to outer dimension to area to volume to mass to cost. Now, I think that's all we should do right now. And I honestly, I wasn't really prepared to talk. I mean, I'm prepared to talk about it, but I have better graphics to show you about the moment of inertia. So let's just consider this the first email. Don't worry about the time frame. And ask me questions one or two at a time. Send me an email at any time. As soon as, whenever I get it and have time, I'll respond with a very quick video showing you exactly what you need to know. That way I'll go and find the right videos or whatever I need, and then we'll get through this. So keep working on it. There's no time frame right now. Don't worry about that. Though I do know you need to worry about your time management. I agree. Not worry, but you need to. That's something to work on. So I don't want to completely leave you adrift. But don't. There's no grade penalty. Keep working on this. Ask me questions through email. I'll answer them with very short videos next time. Okay? Let me know if you get that and if you agree.